Now I am going to discuss with you the output equation. What is the power input? Power input we are giving to that stator supply is 3 times phase voltage into phase current into cos theta into 10 to the minus 3 kilowatt. That means 3 VPH IPH cos theta into 10 to the minus 3 kilowatt. Power output we are getting, that is 3 VPH IPH cos theta into eta. Eta is the efficiency into 10 to the minus 3 kilowatt. Neglecting the stator voltage drop, VPH equals to EPH. So the power output will be 3 times phase EMF into phase current into cos theta into efficiency into 10 to the minus 3. Once again I am repeating, the power output equals to 3 into EPH into IPH, that is phase current, into cos theta power factor into efficiency into 10 to the minus 3. So induced EMF equals to EPH 4.44 frequency into flux into number of turns per phase into kW. Induced EMF equals to 4.44 F phi TPH into kW. Now output equation. What is the output equation? Synchronous speed Ns equals to 120 F by P, that is the unit will be in RPM. So 120 F by P, F is the frequency and P is the number of pole. So synchronous speed equals to 120 into F by P RPM. In this way we can derive the output. We can derive the power output by just keeping the value and adjusting all the values and keeping the constant in mind and substituting this value in the equation. You can easily get the power output equation. Now, what is a specific loading? Specific magnetic loading is average flux density over the air gap. It is the average flux density over the air gap, that is B average. That is equals to P phi by pi dl. P phi is the pole and phi is the flux. Pi is the pi 22 by 7, that is the pi constant, and d is the you can say the diameter of that stator, diameter of that, and L is the length of the stator. So specific loading is average flux density over the air gap. Now specific loading, a specific electrical loading, what is that? What is a specific electrical loading? So specific electric loading is the number of stator ampere conductors per meter length of a stator periphery. Number of stator ampere conductors per meter length of a stator periphery at the air gap, that is denoted by AC, equals to Ziz by pi d. Once again I am repeating, what is a specific electrical loading? Number of stator ampere conductors. Stator ampere conductors per meter length of a stator periphery. Per meter length of a stator periphery. Stator periphery के जो है per meter length में कितने number of stator conductors हैं, that is called a specific electrical loading. So you can also find out the final equation and you can just get the output constant by keeping the value BAV, that is the specific magnetic loading, equals to P phi by pi dl, and AC, that is Ziz by pi d. So by keeping the substituting this value to that in equation, you can get the output power in terms of diameter of this periphery. And so now design Q, the output equation, that is equals to C naught into D square LNS. The quantity dl square ln is related to the volume of the machine. The quantity dl square ln is related with the volume of the machine. So, one main criteria for good design is reduction in the volume of the machine. The most important thing is in the design of the machine is reduction in the volume of the machine, that will result in saving the cost of the material, saving the transportation cost. So, these two benefits are very important, but that is related with the volume or the volume, volume of the machine. Thus, we can say that the output power Q equals to C naught into D square Ln. Volume D square L can be reduced if C naught is increased or Ns is increased. So, by increasing both the things, the volume of the machine can be decreased. So, we will discuss more about C naught, that is the constant. Kw is the constant. So, how we can just increase the specific magnetic loading, specific electrical loading, and how we can changing these parameters, we can have a very clear picture of design of that machine. So, specific loading P5 pi dl. What is the advantage of increasing BAV? Size of the machine will get reduced and the cost of the machine will get automatically decreases. This is the advantage, but what is the disadvantage? We know that everything has advantage and disadvantage. So, what is the disadvantage of increasing the BAV? Magnetizing current will go up. When we will increase the BAV, then the magnetizing current will go up, the core loss will go up, power factor become poor, the power factor will become poor, and the temperature rise will increase. Temperature rise will increase. So, the optimum value which is defined is 450 Hz machine, BAV equals to 0.35 to 0.6 Tesla. What is the impact of changing the AC? What is the impact of changing the AC? That is a specific electrical loading. What is the impact of that? Advantage of increasing AC is size of the machine will get decreased and the cost of the machine will get decreased. So, two advantages, the major advantage, the size will get decreased and the cost of the machine will decrease, and it will save the transportation cost also. What are the disadvantages of increasing this AC? So, higher amount of copper will be there. The higher disadvantage will be a higher amount of copper will be used. More when the copper will be used, the quantity of copper will be higher, then the copper losses will be higher, and there will be the increase in the temperature rise and efficiency of the machine will get decreased. So, once again I am repeating, advantage of increasing AC is size of the machine will get decreased and cost of the machine will get decreased, and it will decrease the transportation cost. Now, if we will talk about the disadvantage of increasing the AC, then the high amount of copper will be used and which will result in more copper losses and the rise in the temperature, increase in the temperature rise and efficiency get reduced. So, the optimum value is defined for the normal range is 5000 to 45,000 ampere conductor per meter. So, for today we conclude our lecture on this, and we will continue from here in the next class. Thanks a lot.